Welcome to the module of the course mass transfer operations. In this module, we will be discussing the pressure driven membrane based separation processes. So, myself Shishendu De, I am from Chemical Engineering Department, IIT Kharagpur. So, in this course, we will be looking into different types of separation processes. Mainly, there are two types of separation processes available in different process industries. One is the equilibrium governed separation process, another is the rate governed process. In equilibrium governed separation process, the equilibrium between the product stream and the inlet stream will be governing the process, and the typical operations like unit operations like distillation, absorption, adsorption, they are typically the equilibrium governed separation process. The major problem in the equilibrium governed separation processes are that the process efficiency is limited by the equilibrium. The composition cannot go beyond the equilibrium composition. On the other hand, there is another separation process, generalization is there, that is the rate governed separation process. These membrane based separation processes are typical examples of these rate governed separation processes. Now, in rate governed processes, the transport rate of a species through the media is the major issue, and that can be really controlled by controlling or tuning the operating conditions like pressure difference, flow rate in the channel, in the flow channel, so on and so forth, concentration, so on and so forth. So, therefore, in the rate governed separation processes, the limitation is the operating conditions. So, if the operating conditions will be of to the extreme cases, so then the process will be limited by that. Otherwise, one can tune and control the transport rate of various species through the separating medium by controlling the operating conditions. Next, I will be talking about we will start with the membrane based processes. So, let us first find out what a membrane is. Membrane is nothing but a semi permeable barrier between two solutions that allows preferential transport of species. So, if there are two components, one component will be allowed to pass or permeate through the membrane, the other component will be retained by the membrane. So, there will be two streams, the feed will be divided into two parts. One is known as what is retained is known as the retained stream, and what is permeated through the membrane is known as the permeate stream. Now, let us look into what are the typical material or construction of membrane. Membrane can be prepared of two components, either organic or inorganic, and typical inorganic membranes are made of various polymers like cellulose acetate, polyamide, polysulfone, so on and so forth, polyurethane, polyacrylonitrile. So, these various polymers are used to prepare the organic membrane. On the other hand, the inorganic membranes are produced by ceramic, alumina, zirconium, so on and so forth. Now, in both cases, in both types of membranes, organic or inorganic, there are certain limitations and advantages. So, in case of organic membrane, the advantage is that one can go very fine pore size of the membrane. So, that means controlling of the pore size will be very accurate and can be done by using the polymeric membrane. For example, one can go down to a level of in the angstrom level pore size in case of the polymeric membrane. But the flip side of the polymeric membrane is that you cannot go beyond a particular temperature, because every polymer will be having can have some temperature. Up to that point it can withstand. Beyond that particular point, the polymer may degrade. So, therefore, one cannot process a stream having a very high temperature using a polymeric membrane. On the other hand, in case of inorganic membrane, the ceramic, alumina, zirconia, etc., the attainment of low pore size is not very feasible. So, therefore, the pore size typically in inorganic membranes are in the micron range. One can again have a coating of polymer over the inorganic membrane, inside surface of the inorganic membrane, and can reduce the pore size, but again that will be limited by the polymeric membrane at the which is appearing on the skin of the membrane. Now, in case of a pure inorganic membrane like ceramic or alumina based membrane, which will be having a pore size in the order of micron, any process stream which will be having a very high temperature can be utilized, can be processed by the inorganic membrane. So, that is the advantage of the inorganic membrane, but the major disadvantage is that we cannot go below the micron range or higher nanometer range pore size in case of inorganic membrane. For a typical, so this slide shows the typical cross section of a membrane. In the membrane, on the top of there is a skin region. This is a dense region which will be having pores of small sized pores. So, this is known as the skin of the membrane. So, this is the cross section of the membrane, and this skin region is having a thickness of around 5 to 10 micron. And sometimes it is as high as 20 micron also. So, since this skin is almost is very dense, the actual separation is done by this by the skin of the membrane, and the base region which will be having in the cross section of the polymeric membrane, it will be containing the macrophoids. So, those macrophoids which are having the highly porous network. So, they will be allowing the transport of the solute through the membrane matrix. So, skin is having two functions. So, first it will be controlling the selectivity of the solutes, because the pore size will be extremely small. Secondly, the thickness of the skin of the membrane is very important as far as the throughput of the membrane is concerned. If a membrane is having a lower thickness of the skin, the resistance offered against the solvent flow through the membrane will be less. Therefore, one can expect very high throughput if the skin of the membrane is skin thickness is very small. On the other hand, if the skin thickness is large, then the throughput will go down. Next, we will be looking into the as I have said in the earlier slide, the materials can be polymeric or it can be inorganic like ceramic and alumina, and the disadvantage of the metallic membrane or the ceramic or alumina type of membrane is the attainment of low pore size, but one can process a stream of high temperature. That is the major advantage. Next, we should understand what the process of osmosis, natural osmosis is defined. Suppose I am having two chambers separated by a perfectly semi-permeable membrane. What is a perfectly semi-permeable membrane? It is basically a polymeric phase or a phase which allows the solutes, which allows the solvent to permeate through it, but it does not allow the solute to pass through it. So, there is a perfectly semi-permeable membrane. In fact, 100% perfect semi-permeable membrane may not be available, but one can really attain a high selective semi-permeable membrane to a tune of 95 to 98%. Okay. So, suppose we are having a chamber which is separated by a semi-permeable membrane in the middle, and in one chamber we are having the solvent is pure water, and in another chamber we put a solution. This solution may be a sugar solution or a salt solution. Now, let us see what happens in the long term. So, since this membrane is a perfectly semi-permeable membrane and solvent is having the, let us say water molecule is having the they are having the smaller pore size, they are freely permeable through this membrane. On the other hand, in case of solution, let us say sugar or salt, they are not allowed to be permeated through the membrane. So, therefore, water will be from the solvent side, it will be permeating through the membrane and coming to the solution side. So, in effect, what happens in the long term, the level of water in the solvent side will go down and level of liquid in the solution side will go up. And how long this will continue? these will continue till the equilibrium is reached. And what is the equilibrium? And the equilibrium will be reached when the water activity on both sides will be equal. So, typically the equilibrium, the time required to attain the equilibrium is more than 24 hours. So, after equilibrium, the water level in the solvent side will go down and the liquid level in the solution side will go up, and that will create a hydrostatic pressure. There is the rho gh, the hydrostatic pressure, and it is known as the osmotic pressure. So, therefore, the osmotic pressure, if I have a solution of different concentration, how the osmotic pressure will behave? If I have a solution of different concentration, this solution will be having a more, this will be more thirsty for water. So, therefore, more water will be passing from the solvent side to the solution side. So, therefore, the osmotic pressure buildup will be more in case of solution having higher concentration. So, therefore, osmotic pressure is definitely a function of concentration. So, therefore, osmotic pressure is known as a colligative property. So, a solution having more concentration of the solute, it is more thirsty for water. So, therefore, it will be having more osmotic pressure. In case of reverse osmosis, so this is a process of natural osmosis. In case of reverse osmosis, we would like to reverse this process. That means, in case of reverse osmosis, we will be applying pressure in the solution side. Suppose you are having a saline solution, that is the salt plus water, and we apply pressure on the solution side, and we should overcome the corresponding osmotic pressure of this solution, and then the first drop of water will be driven out from the solution side to the solvent sides. So, it is known as the reverse osmosis. So, therefore, the major problem of the reverse osmosis, as we have understood, that to overcome the osmotic pressure of the solution. So, typically for a seawater, the water salt concentration is around 30,000 ppm, that is 30 gram per liter or 30 kg per meter cube. That will be corresponding to a very high osmotic pressure to around 25, minimum 25 atmosphere. So, therefore, one has to apply very high pressure beyond 25 atmosphere in order to realize the first drop of water driven out from the solution side to the solvent side. So, therefore, reverse osmosis is basically an energy intensive process. Okay. So, next we will be looking in this slide, I have listed some of the typical characteristics of membrane separation process. So, in case of membrane separation, the major advantage is there is no phase change. We are not changing the phase of the medium either from the liquid to vapor or vapor to liquid. So, there is no phase change is occurring. So, therefore, it is less energy intensive compared to any process involving phase change like evaporation. Since there is no phase change, the large amount of latent heat involved in the process is not required. So, therefore, it is less energy intensive, and it is low temperature process. So, we can carry out the operation under normal room temperature conditions. So, it is a low temperature process. We do not require to add any additive. It is entirely a physical separation process. There is no additive in this case, and we are not adding any chemicals from outside, and separation is mostly based on the molecular weight or that will be proportional to the size of the solute, and this is very easy to scale up. So, therefore, we can go for a scaled up version which can handle larger throughput of the process. Okay. So, there are two types of membranes. One is the homogeneous membrane, another is the homogeneous or symmetric membrane, another is the asymmetric membrane. In case of homogeneous membrane, the pore size distribution in the membrane is more or less homogeneous. So, therefore, on the other hand, in case of asymmetric membrane, there is a thin skin. If you look into the cross section of the membrane, there is a thin skin on the top of it, and which will be very, very dense, followed by a subsurface or base which will be having larger diameter pore size. So, this thin skin is basically controlling the selectivity of the membrane and also throughput of the process. lower be the skin thickness, higher be the throughput as we have discussed earlier, and larger be the skin thickness, lower be the throughput. So, therefore, by discovery of the asymmetric membrane, the membrane based separation process becomes feasible because it can handle larger amount of throughput. Now, let us look into the typical membrane casting steps. There are two types of membranes as we will be talking about in its configuration. One is the flat sheet membrane and there is the hollow fiber membrane. In case of flat sheet membrane, the preparation method is known as casting. On the other hand, in case of hollow fiber membrane, the preparation method is known as the spinning of the membrane. Now, let us look into different steps, typical steps for membrane casting processes. First, one has to select a polymer, that is the cellular acetate or polyacrylonitrile or polyethylene or polysulfone or polyether sulfone. We have to select a particular membrane and a solvent system, and the solvent can be acetone, it can be DMF like dimethyl formamide, it can be DMSE, it can be DMSO. There are typical solvents available for different polymers, this type of polymers, and selection of the polymer and solvent is very, very important because that will be deciding the interaction between the polymer and solvent, whether you will be getting a denser membrane, whether you will be getting a more open pore size membrane. That will be decided initially by the choice of polymer and the solvent system. So, first we will be selecting a polymer and solvent, dissolve the polymer at a particular concentration in the solvent, forming a viscous solution. Then this will be placed between two glass plates. The top plate is given a one dimensional shear, leading to a formation of very thin film on the bottom plate, and the lower plate is kept in ice water and the film is detached. So, then before that there will be evaporation of the solvent. Evaporation of solvent will take place and that will be forming the minute pores, and when the polymer film is put into water, water being anti-solvent to the polymer, whenever there will be interchange of solvent and anti-solvent, the solvent that will be using either DMF or DMSE and the water, because of the interdiffusion, water will be penetrating into the polymer matrix and solvent will be coming out, and whenever the water that is getting into the polymer system, water being anti-solvent to the polymer, whenever water touches the polymer, immediately polymer gets solidified, forming the fine pores in the polymer matrix. Therefore, a porous network will be produced. So, therefore, the solvent non-solvent interaction is very, very important, and then generally heat treatment or annealing is done to 70 to 80 degrees centigrade to form a stable sheet of membrane, and for a flat sheet membrane it is like a A4 size paper. Now, let us categorize different types of process, membrane based processes. There are 4 types of pressure driven membrane based processes. First one is the reverse osmosis, then nanofiltration, then ultrafiltration, and finally, we will be having the microfiltration membrane. In case of reverse osmosis, the striking features is that osmotic pressure plays a very, very important role in case of reverse osmosis, as we have already discussed. The pore size of the membrane is 2 to 10 angstrom. That is the typical pore size distribution in case of reverse osmosis. The operating pressure requirement is very, very high, as we have discussed earlier in the case of during the definition of osmosis process. The sea water contains around 30 kg per meter cube salt solution that will be giving rise to very high osmotic pressure. So, in order to get a very high, quite reasonable throughput of the process, one has to overcome the osmotic pressure. So, therefore, the operating pressure requirement in case of reverse osmosis is 25 to 40 atmosphere. And a very good reverse osmosis means more than around 95% separation of monovalent salt sodium chloride. So, what are the applications of reverse osmosis? Production of potable water from sea water, production of low salinity from industrial use, recovery of whey protein. And typical transport mechanism in reverse osmosis is known as permeation, and permeation mechanism has 3 different steps: dissolution of solute from the feed site to the membrane polymer matrix, then diffusion of the solute through the polymer matrix, and desorption to the permeate site. Then comes the operation nanofiltration, in case of nanofiltration, the pore size is slightly larger, 10 to 20 angstrom, and the operating pressure requirement is less, 10 to 25 atmosphere, because in case of nanofiltration we are trying to separate out the the dyes, the polyphenols and solutes which are having the molecular weight between 200 Dalton to 1000 Dalton. And since the osmotic pressure is inversely proportional to the molecular weight of the solute, so if you increase the solute molecular weight or size, the osmotic pressure requirement is goes down. So therefore, the operating pressure requirement in case of nanofiltration is less, it is around 10 to 25 atmosphere. And a good nanofiltration membrane indicates separation of the monovalent salt to a tune of 65 to 80%, and molecular weight of solutes to be separated between 200 to 800 Dalton. So applications of nanofiltrations are dye removal of whey protein, production of softened water for industrial use. It is used as a pre-treatment to reverse osmosis, and the transport mechanism is permeation, which we have talked about earlier in case of reverse osmosis, having 3 steps: dissolution, diffusion and desorption. In case of ultrafiltration, it is the most versatile operation. It has a wide distribution of wide range of pore size from 20 to 100 angstrom, and in case of ultrafiltration we are basically separating protein, colloid, high molecular weight solute. So therefore, osmotic pressure of these solutes of these solutions corresponding to this solute will be extremely small. So the operating pressure requirement is very small. In case of ultrafiltration, it is 6 to 8 atmosphere, and molecular weights of solutes to be separated is in the range of 1000 to 1 lakh Dalton. And transport mechanism that is involved in case of ultrafiltration is diffusion and convection. So it has a found high applications in separation of high molecular proteins, colloids, polymer, clarification of fruit juice, in hemodialysis, so on and so forth. In case of microfiltration, we are dealing with pores in micron range. It should be 0.1 to 5 micron, and the operating pressure is 2 to 4 atmosphere, because the sizes of the solutes, those are separated by microfiltration membrane, will be extremely high. So therefore, the osmotic pressure will be almost non-existent. So you will be having a very low operating pressure, 2 to 4 atmosphere, and molecular weight of solutes to be separated beyond 1 lakh Dalton. So transport mechanism is mainly convection, because we are talking about the larger pore size, where the role of diffusion will be minimized and the convection will be predominant, and applications will be separation of very high molecular weight proteins, clay, pigment, red blood cell, so on and so forth. Now, once we have the different types of membranes, then let us characterize the membrane. Membrane will be having typical 2 characteristics. One is how porous my membrane is, and second is how selective my membrane is. How porous my membrane is, that is denoted by the permeability of the membrane. It has a direct relevance to the throughput of the process. So if a membrane is highly permeable, that means it can handle large throughput through it. And and second is the selectivity of the membrane. How selective my membrane is, that is defined by this parameter retention. And selectivity is basically if the membrane is highly porous, then it loses its selectivity, and so therefore this permeability and selectivity retention, they are inversely related. And there are 2 types of how the permeability will be measured. Permeability will be measured by conducting experiments with pure distilled water, because in case of pure distilled water we do not have any solute. So therefore there is no osmotic pressure in the solution. So the permeate flux or the throughput of the process, that means that amount of volume of filtrate that is generated per unit square meter of membrane per unit time is known as the permeate flux. So we set different operating pressures and measure the permeate flux in the membrane separation apparatus, and measure the permeate flux for different transmembrane pressure drop and plot them. And since there is no osmotic pressure, this plot will be going through the origin, and it will be linear, and the slope of this curve will be giving you the permeability of the membrane. By looking into the order of magnitude of the permeability of the membrane, one can understand what typical process will be looking into. For example, if the order of magnitude of this permeability is 10 to the power minus 12 SI unit, then we will be talking about a reverse osmosis membrane. If this permeability is in the range of lower molecular weight, lower range of 10 to the minus 11, higher range of 10 to the minus 12 and lower range of 10 to the minus 11, then it will be a nanofiltration membrane. If it is in the order of 10 to the minus 11 higher range, then it will be an ultrafiltration membrane. If it is in the order of 10 to the minus 10, it is basically a microfiltration membrane. And real retention can be retention of the membrane can be measured by conducting an experiment under high stirring speed, low concentration and low pressure. Whatever the under this condition, the concentration is uniform in the feed channel, and whatever the observed retention in this case is equal to real retention. Then molecular cutoff is another characteristic of the membrane, which is an easy way of rating of the membrane. Membrane will be having different types of pores, and it will be having a pore size distribution. So, therefore, it is very difficult to evaluate the pore size distribution in the membrane. So, the easy way of average pore size of the membrane is molecular cutoff. So, how we calculate the molecular cutoff curve? We conduct experiments of different solutes and then measure their retention and plot retention versus molecular weight in the semi-log plot, and the corresponding to 90% retention, we find out the molecular weight, and that molecular weight is the molecular weight cutoff. So, a membrane with 20,000 molecular weight cutoff means it retains solute of molecular weight 20,000 and above, and it allows to permeate the solutes of molecular weight less than that. What is the driving force of the transport? Chemical potential gradient across the membrane is the major driving force, and chemical potential is a function of pressure, temperature, concentration. So, by changing one or more of these independent parameters will be the will cause the solute and species transport across the membrane. So, membrane fouling is very important in a process. There will be two types of fouling. One is the reversible fouling, another is the irreversible fouling. In case of reversible fouling, the solutes will be deposited over the membrane, and this fouling can be removed by external washing. So, that is why it is known as the reversible fouling. In case of irreversible fouling, some of the pores are clogged or blocked by the solute particles, which cannot be removed by even after an efficient washing protocol. So, there will be a permanent loss of the membrane and the corresponding permanent loss of permeability of the membrane, and corresponding fouling is known as the irreversible fouling. Now, let us come to the membrane modules. There are 4 types of modules: plate and frame module and tubular module. So, these are having the high cross flow velocity, they can process high suspended solids. Then hollow fiber module. These hollow fiber modules are basically large number of fibers are packed inside a bigger diameter of pipe, and therefore, the solvent will be feed will be passed through the lumen, and the filtrate will be coming out from the surface. So, definition of this the major criteria of designing these modules is to attain the larger surface area in a smaller volume, so that the design becomes very compact. Next one is the spiral wound modules. In case of spiral wound module, one have the flat sheet membranes, and these membranes will be wound spirally along the central axis, forming the spiral wound module. So, high surface area in a small volume is the key point. So, this is a typical configuration of a cross flow module system. So, in this case of cross flow, there will be deposition of the, so there will be convection towards the membrane surface, there will be backward diffusion from the membrane surface to the bulk, and there will be convective flux from the surface to the permeate stream. So, in a typical steady state operation, all these fluxes will be equal, forming the governing equation. So, major problem is the deposition of the solutes of the membrane surface, forming the, and this is known as the concentration polarization, because the solutes will form are polarized, they will be forming a sort of mass transfer boundary layer on the membrane surface. Larger the thickness of this concentration polarization layer, more resistance it will be offering against the solvent flux. So, therefore, this decreases the throughput of the process, increases the fouling. So, concentration polarization is not at all desirable in case of a membrane system. So, net driving force is reduced by osmotic pressure built up, and it is decreasing the throughput of the process. So, these are the some of the consequences of concentration polarization. If membrane surface concentration increases, osmotic pressure increases, or net driving force increases. So, this will reduce to reduction in the throughput of the process. Viscosity also increases because viscosity is the strong function of concentration. So, that increases the resistance against the flow and the flux is reduced. Similarly, membrane surface concentration can be so high that it form a very thick layer of solutes over the membrane surface, forming a gel type of layer that will offer extra resistance against the flux, against the solvent flow, reducing the throughput of the process. Similarly, concentration polarization will promote diffusion through the membrane surface, that will membrane matrix, that will lead to clogging of the pores, that reduces the membrane permeability. So, the result is decline in the permeate flux. So, all these manifestations of concentration polarization are leading to reduction in permeate flux. So, control of the concentration polarization is very critical in this process. So, let me just give some steps of modeling process. First, there will be a solution of fluid dynamics and mass transfer outside the membrane. So, there will be, we divide the whole process into two terms, that is the flow outside the membrane, flow inside the membrane. So, solution of fluid dynamics and mass transfer outside the membrane, and then obtain the appropriate transport law inside the porous membrane. Then coupling of these two processes will be leading to a system performance. So, film theory is used, as we have said, the total flux to the membrane at steady state will be 0. That will give rise to the equation which will be basically defining the concentration polarization, and the mass transfer coefficient can be obtained from either the flow regime is laminar or turbulent, and we can get the mass transfer coefficient. So, by solving, so there are for rectangular channels, the Sherwood numbers are available from the laminar flow. For the turbulent flow, Dieters-Bolter, for the laminar it is a Liebig relation, and then this equation can be simplified for case number 1, no concentration polarization or low polarization, and low polarization, but perfectly rejecting membrane. So, otherwise the whole equation can be solved by solving this set of equation. The film theory, that will be defining the concentration polarization in the outside of the membrane, osmotic pressure relationship, that is permeability multiplied by the delta P minus delta pi, and delta pi is a function of concentration. In case of reverse osmosis, solution diffusion model is used for transport law through the membrane, and for ultrafiltration it is a definition of real retention, which is nothing but a trial and error solution between membranes. So, real retention is basically a partition coefficient of solute across the membrane on the feed side and the filtrate side. By solving these three set of equations, one can do a trial and error solution. I can get a performance of the process, that is Cp is the permeate concentration of the solute, and Vwa is the permeate flux of the process. So, therefore, throughput and selectivity of the process both can be predicted by doing a trial and error solution of these three equations. For the case of reverse osmosis, one has to use the solution diffusion model, and for case of ultrafiltration, one has to use the definition of real retention. In this case, B is basically the fitting parameter. In the case of ultrafiltration, real retention can be estimated by a separate set of experiment. In fact, some of the cases B can also be estimated by a independent set of experiment, and as we have discussed, the permeability of the membrane can also be independently measured by conducting the experiment with the pure distilled water. So, therefore, one can get a predictive model. It is basically a one dimensional predictive model for definition of the system performance. So, roughly, so these will be the basic striking features and modeling characteristics of a typical pressure driven membrane based separation process. So, we will stop here at this point. If anyone of you is interested in having more insight and of the membrane based separation process, later on we can discuss and they can contact me as well. Thank you very much for your kind attention.